All right, so this is a review for multivariable calculus or calculus 3 course. We're doing an exam review for a couple chapters that involve vectors and lines and planes and just sort of general introduction to three-dimensional space. I'm just going to go through some problems here. First problem, we have vector A is 3, negative 1, 4. Vector B is 1, negative 1, 0. And then we're supposed to just do some routine calculations. So the first one is 2A minus 3B. Here. So 2a is 2 times the vector 3, negative 1, 4, minus 3b is the vector 1, negative 1, 0. Now when we multiply a vector by a scalar, we just sort of distribute this 2 to each of the 3, negative 1, 4, and this 3 to each of the 1, negative 1, 0. So what we get, here's 2 times 3 is 6, 2 times negative 1 is negative 2, 2 times 4 is 8, minus 3 times 1 is 3, 3 times negative 1 is negative 3, 3 times 0 is 0, and then the subtraction with vectors is just component-wise. So we get 6 minus 3, that's 3, negative 2 minus negative 3, it's negative 2 plus 3, that's 1, and we get 8 minus 0, that's 8. So our answer here is the vector 3, 1, 8. Next question, we've got A dot B, so that is 3, negative 1, 4, dotted with 1, negative 1, 0. And now we just want to do a dot product here. So what the dot product does is we take the first component of A times the first component of B, 3 times 1, second component times second component, and we're going to add that. So plus negative 1 times negative 1, plus 4 times 0, third components. Here, and what we get with our dot product is going to be a scalar. 3 plus 1 plus 0, that works out to be 4. Next question, we're going to do a cross product. Cross product of two vectors should give us another vector back. Got our A and B written down up here. So we're looking for 3, negative 1, 4, crossed with 1, negative 1, 0. So there's a few different ways to sort of do the bookkeeping for this calculation. I like to do this as a determinant of matrices, or of a matrix. We have I, J, K, go up here, and I put the first vector, 3, negative 1, 4 in the second row, and the second vector, 1, negative 1, 0, third row, and then I'm going to do a cofactor expansion along the first row, and get I times the determinant of negative 1, 4, negative 1, 0, so that's negative 1 times 0. I'm going to cross out the column and the row. I'll just write that out. Negative 1, negative 1, 4, 0. And then it's a minus j times cross out the column and row of j. Get a 3, 1, 4, 0, 2 by 2 determinant, and plus k. Note we get a plus I and a minus j and a plus k. And we get a 3, negative 1, 1, negative 1. And these just work out to be, see, negative 1 times 0 is 0, minus 4 times negative 1 is plus 4. So we get 4i. So we have 3 times 0 is 0. 4 minus 4 times 1 is 4. We're going to subtract 4. This determinant is negative 4. The negative out there makes this a plus 4j. The k is 3 times negative 1 is negative 3. Then we're going to subtract a negative 1. That's going to give us a minus 2k. So you could leave your answer like this. That's fine. In vector notation, maybe the other notation we're using, I would write this as 4, 4, negative 2. Note, if you want to check this, you can take a dot product of this vector with both of these, and individually 4, 4, negative 2, dotted with 1, negative 1, 0, should give you 0. That is, they should be perpendicular or orthogonal. 4, 4, negative 2, dotted with 3, negative 1, 4 should also give you 0. So if you do 4 times 1, that's 4. Negative 1 times 4 is negative 4. Well, I'd get a 0 for sure. 4 times 3 is 12. Negative 1 times 4 is negative 4. Those add to 8. Negative 2 times 4 would give us a negative 8. That would give us a 0 as well. So the answer checks out. Okay, now the magnitude of A. So A was the vector 3, 1, 4. We do the magnitude of a vector. Sorry, 3, negative 1, 4. What we do is we take the square root of, we take the first component squared plus the second component squared plus the third component squared. If you think about it, this is really the square root of A dotted with A. And in our case, that is, let's see, square root of 9 plus 1 plus 16. 9 plus 1 is 10, plus 16 is 26. So we get a square root of 26 as our answer. Next up, we want to find a unit vector in the direction of b. Just write down b was 1, negative 1, 0. So b happens to be 1, negative 1, 0. And we want to find a unit vector that points in the same direction. So what we're going to do, the standard sort of operation to get our unit vector, call that u, is you do b divided by the magnitude of b. So it's the vector 1, negative 1, 0, divided by the magnitude of 1, negative 1, 0. So that's 1, negative 1, 0, divided by the square root of 1 squared plus negative 1 squared plus 0 squared. So that's 1, negative 1, 0, divided by, this is going to work out to be 1 plus 1 is 2, plus 0, square root of 2. And you can take a vector, divide by a scalar, and sort of do that component-wise. And so we get 1 over the square root of 2, negative 1 over the square root of 2, 0. You could rationalize denominators, multiply by square root of 2 over square root of 2 if you want to. I think this answer is fine. If you wanted to rationalize that, you'd get square root 2 over 2, negative square root 2 over 2, and 0. Okay. Angle between A and B. So you have two vectors. You want to find the angle between them. What we're going to use is the formula A dot, A dot B is the magnitude of A times the magnitude of B times cosine of theta, where theta is the sort of angle between the two vectors. So rearranging this, we get theta should be an inverse cosine of A dot B over magnitude A times magnitude B. We get an inverse cosine, arc cosine, A dot B. I believe we found that already up here. You could run the calculation again. But A dot B was 4. A dot B is 4. Magnitude of A was one of the particular questions here. I believe that's the square root of 26. Magnitude of B, let's see. Well, we used that to find the unit vector. The magnitude of B was the denominator here. That was the square root of 2. You could also just run through these calculations on your own. Note, if I simplify this, I get cosine inverse of 4 over 2 square roots of 13. I could factor out a 2 from the 26 and do 2 times 2 is 4, square root is 2, which works out to be cosine inverse of 2 over square root of 13. So that's a fine answer. You could convert that into degrees or radians with an approximation using a calculator if you'd like to. Okay. Now we want to find the area of the parallelogram determined by A and B. So we've got a parallelogram, A, B. We want to find the area. That area, one way to calculate that is you take A cross B and you find the magnitude of A cross B. So we could go back through our calculation for A cross B. We could just redo that. In this case, I'm just going to copy that over. So A cross B, so this one here, it's 4, 4, negative 2. So again, if you hadn't done that question already, you could just redo this. It's 4, 4, negative 2. So I just need to find the magnitude. It's the square root of 4 squared plus 4 squared plus negative 2 squared. It's the square root of 16 plus 16 plus 4. 16 plus 16 is 32, plus 4 is 36. Square root of 36. We get an area of that parallelogram of 6. Next one. Find a vector projection, find the vector projection of A onto B. So if we recall, again, A was 3, negative 1, 4. B, our vector, I believe it was 1, negative 1, 0. I want to just check that. Yep, we've got a 1, negative 1, 0. Whoops. Not where it was. -1, -1, 0 for b. And we do this projection here of a onto b. The picture, when you look at this, is you've got a vector here. Let's see, this vector is a, and then there's some other vector b here. And what we're looking for is really this vector here, where we get a right angle. So that red vector is the projection of a onto b. So that's really what we're looking for here. And the formula for that, so we're going to do a projection of onto 1, -1, 0. We're going to project 3, -1, 4. That formula is I'm going to dot my two vectors, 3, -1, 4, dotted with 1, -1, 0. And I'm going to divide by the magnitude of the vector I'm projecting onto. That's b, or 1, -1, 0 in this case, but that magnitude squared. And then I'm going to multiply by the vector 1, -1, 0. So this is going to give me a vector. This really gives me some sort of multiple of this vector here. So we're going to get, oh, sorry, I actually messed up my projection here. I have to go back. Looking at this, this is not the projection of a onto b. Whoops. Well, let's draw a in here again. So a goes here. What we want to do, we do want to drop this perpendicular, but a projection of a onto b should be in the direction of b. So I messed that up there a bit earlier. So we get this projection here. And you'll notice here what I was thinking of is that what I'm getting is a multiple of b, 1, -1, 0, so that vector should point in the same direction as b, or perhaps in the opposite direction. This sort of perpendicular vector should dot to 0 with b, but that's not going to happen here. Okay, now we need to do the calculation. We get 3 plus 1 plus 0, that's 4 when we do the dot product. This bottom is going to be 1 squared plus -1 squared plus 0 squared. We're going to multiply that by 1, -1, 0. So we're going to get 4 over 2 on the bottom times 1, -1, 0. That's 2 times 1, -1, 0. So that gives us the vector in the end, 2, -2, 0. So that's really this red vector here. Okay. Now that was projection, vector projection. Let's find the scalar projection of a onto b. So the scalar projection, all this is when it's scalar projection, is it's really the magnitude of the projection of a onto b. So you could, given that we have the vector projection, just take the magnitude of that vector. That would be fine. Another calculation here is you could say this is a dot b divided by the magnitude of b. Note, not squared like we did up here, but we just have one b there. Essentially, we're using the other b to change this, oops, sorry, the other magnitude of 1, -1, 0. Take this minus one of those to get a unit vector here. And we need an absolute value of a dot b as well, because a dot b could be negative. So in our case, what we get is a dot b is 4. Magnitude of b is square root 2. So we get 4 over square root of 2. It's probably an okay answer. It might be a good idea to multiply top and bottom by square root 2 to rationalize that denominator. So we get 4 square root 2 over 2, which is 2 square roots of 2. So the scalar projection of a onto b is 2 square root of 2. Note that's going to be the same thing as the magnitude of this 2, -2, 0, of the vector projection. Okay, so end of that a and b vector calculations. New question. We want to find the equation of the line containing the points 3, -1, 4, and 2, -1, 0. So when we say the equation, this is going to be a parametric equation. And so the general setup here is we're going to just do an r of t. What we're going to get is pick one of the points. It doesn't actually matter which one. I'm going to pick the first one. So you can take the point plus multiples of the vector between the 2 points. And the way you get that vector is you're going to subtract component-wise. So let's do 2 minus 3, that's -1, -1 minus -1 is 0. 0 minus 4 is -4. You could have subtracted in the other way. You could have used the other point here. When you put this all together, what you get, let's see, this is 3, -1, 4. When you distribute the t, you get -t, 0, -4t. You add component-wise, you get 3 minus t, -1, 4 minus 4t. So this is really your parametric equation for the line that contains these 2 points. Note the way we did this. If you plug in t equals 0, you'll get 3, -1, 4, the first point. And if you plug in t equals 1, 3 minus 1 is 2, -1, 4 minus 4 times 1 is 4 minus 4 is the 0. So this is the point when t equals 0. This is the point when t equals 1. Sometimes that's nice to know. Okay, next sort of standard calculation here is we have 3 points, and generally those points will determine a plane. We're going to find that plane. So the first thing we're going to do is let's just write down the points here in a drawing. So we have 3, 2, 1. We have -4, 0, 4. And then we have 0, -1, -2. I'm going to try and find a normal vector to the plane. To do that, I need 2 vectors in the plane. And so I'm going to do at least, well, 2 subtractions here of points. So this vector here, let me write that in red, it's going to be -4 minus 3. That's -7. 0 minus 2, that's -2. 4 minus 1, 3. So the vector from 3, 2, 1 to -4, 0, 4 is -7, -2, 3. That's one vector that's sort of in the plane we want. The other vector from 3, 2, 1 to 0, -1, 2, so 0 minus 3 is -3, -1 minus 2 is -3, -2 minus 1 also -3. So here's another vector that's in this plane. Now, what we need for the equation of plane is we need a normal vector and a point on the plane. We've got 3 points on the plane, so you can pick any one of those. So you only get that normal vector. That normal vector is going to be the cross product of any 2 vectors in the plane. So we're going to take -7, -2, 3, and cross that with -3, -3, -3. So you get, here, let's see, -7, -2, 3, -3, -3, -3. Let's see, in the I component, we get -2 times 3 is positive 6, minus 3 times -3, that's minus -9, so plus 9, that's a 15. For the J component, -7 times -3 is positive 21. 3 times -3 is -9, so we're going to add 9. That's 30, but because it's the J, it's a -30. And then the K would be -7 times -3 is positive 21. Minus 2 times 3 is 6. 21 minus 6, that's a 15. So this is our normal vector, 15, -30, 15. You could now write an equation. You could do 15, a few ways to do this. 15 times, let's pick the point 3, 2, 1 here, sort of arbitrarily pick a point. 15 times x minus 3 minus 30 times y minus the 2 plus the 15 times z minus 1, and then that should equal 0. So essentially we're saying the vector 15, -30, 15, and the vector x minus 3, y minus 2, z minus 1, if you take the dot product of those 2 vectors, you should get 0. So the 15, -30, 15 is a normal vector. X minus 3, y minus 2, z minus 1 is some random vector in the plane, or arbitrary vector. Now, you could do a couple things with this. You could distribute this out here. Something else you could do is, if you notice this vector, maybe this normal vector, let's do this in a little different way, is you have a factor of 15. So this is 15 times the vector 1, -2, 1. So if 15, -30, 15 is normal to plane, so is 1, -2, 1. So one thing I might have done is just use this smaller vector here to work with. Just makes the calculation easier. There's certain places you could have noticed part of this 15. For instance, you could have rewritten -3, -3 as 3, or even -3 times 1, 1, 1. But still, we got sort of a factor of 5. So if you have the 1, -2, 1, you could rewrite this as just x minus 3 minus 2 times y minus 2 plus 1, which I don't need to write, times z minus 1. It's just a little bit simpler. Another thing you can do with either of these, let's just do the 1, negative 2, 1, is you could solve this here. Let's just do that first. So you get x minus 3 minus 2y plus 4 plus z minus 1 equals 0. That gives you x minus 2y plus z equals, let's see, we have negative 3, negative 1, that's 4, plus 4. That's actually a 0 there. So your point is x minus 2y plus z equals 0. Now, something you could have done once you had your normal vector 1, negative 2, 1 is written this down as x, when it's going to be x minus 2y plus z. It's going to equal some constant. And just to evaluate that, whoops. So evaluate that expression at any of the points here. So let's do 3, 2, negative 1. So 3 minus 4 is negative 1, plus 1, that tells me 0. There. So I don't need to, let's make that a little nicer. I don't need to actually expand this out as x minus 3, y minus 2, z minus 1. I can just plug in 3, 2, 1. 3 for x, 2 for y, 1 for z, and see what I get. Now, the idea is, and a nice check on this, is you should be able to plug in the other 2 points as well. So negative 4 times x plus 0 y, so negative 4 for x, 0 for the y, 4 for the z, negative 4 plus 4 is 0. If you use the point 0, negative 1, 2, you get a positive 2 from the y, minus 2 from the z. That'll give you 0 as well. So you can see this equation is in the form of a plane, and and these 3 points are all on that plane, so that you can know right away is the answer. Okay, next question here. Let's find the equation of the plane containing the line r of t is 2 minus t, 3 plus t, comma 5 plus 2t, and the point 5, 3, 0. So we're finding the equation of a plane. We need a point on the plane, which we have. That's the 5, 3, 0. We also need a vector that's normal to the plane. Now, because this vector is, or this line is in the plane, you can pull off sort of the direction vector of the line. That'll give you a vector that's in the plane, not a vector normal to the plane. So we're going to have to create something else. So our geometry here, let's draw this out. We have our line, and then you have your point 5, 3, 0. Now, this particular vector, or parameterization, if I sort of pull apart the components without the t and then the parts with the t, I get 2, 3, 5, so there's no t's, plus t times negative 1, 1, 2. And if you think about how you construct the parameterization of a line, that means that we have a point on the line, 2, 3, 5. And that means we have a vector in the direction of the line, negative 1, 1, 2. So this vector here is negative 1, 1, 2. Now I don't actually know if that vector goes this way or perhaps in the opposite direction, but it's not going to really matter here. So all of this is in the plane we're concerned about. And so we have to get a normal vector to the plane. We only have one vector, so we have to create a second vector. So that other vector, we can take our 2 points and subtract them. So I'm going to do 5, 3, 0 minus 2, 3, 5. When you do that, 5 minus 2 is 3. 3 minus 3 is 0. 0 minus 5 is negative 5. So now we have a new vector, and then the negative 1, 1, 2 are both in the plane. So we can get a normal vector. Our normal vector should be the cross product of those two vectors. So we're going to do I, j, k, 3, 0, negative 5, and then negative 1, 1, 2. So that will give us a normal vector to the plane. So we'll get our I component, we get a 0 minus negative 5, that's a positive 5. J is going to be 6 minus 5, that's a 1, because j it's a negative 1. K is going to be 3 minus 0, that's a 3. So our normal vector is 5, negative 1, 3, and we have a point 5, 3, 0. So the method that I like to do is just write down 5x minus y plus 3z. I know that should be constant for every point in the plane, in particular for 5, 3, 0. So if we do a 5 times 5, we get 25. minus 3, that's 22, plus 0. So that should get a 22, because if I plug in 5 for x, 3 for y, 0 for z, I get a 22. So that just has to be the right equation. Okay. Another equation of the plane question. So I find the equation of the plane parallel to the plane 3x minus 4y plus z equals 7 and containing the point 3, negative 1, 2. So if I have two planes that are parallel, that's going to mean they have the same normal vector. So our normal vector is the same as the normal vector of this equation. But we can actually just read that off as a 3, negative 4, 1. So parallel planes, we get the same normal vector. So in our case, we're going to end up with an equation like 3x minus 4y plus z. That's the same left-hand side. What's potentially going to change is this right-hand side will be something other than 7. How do we find out what that is? Well, we need to have the point 3, negative 1, 2 on the plane. So you can just plug in 3 times positive 3. 3 times 3 minus 4, our y component is negative 1, plus 2. That gives us 9, plus 4 is 13, plus 2 is 15. That means that the equation is 3x minus 4y plus z equals 15. So that will both include this point and be parallel to this plane. Oops, okay. Another equation, this time for a line. So we find an equation of a line parallel to this line and containing the point 5, 2, negative 1. So two parallel lines will have direction vectors that point in the same direction, or at least the direction vectors will be scalar multiples of each other. So our vector, sort of in the direction of the line, well, that's going to be the things multiplied by t here. So that's a 3, that's a negative 1t. There's no t in the z component, so that's a 0. This is sort of our direction vector. And so our line, let's maybe call this r2 of t. I've used r of t up here, so I want to call it something else. It's going to be the point, which I'm going to sort of write as a vector, 5, 2, negative 1, and then plus t times 3, negative 1, 0. In the end, this gives us 5 plus 3t, 2 minus t, and then just negative 1 here. So note, really, it's very similar to this. We have the 3t, we have the minus t, we have no t's here. And instead of having negative 1, 2, and 4, we have 5, 2, and the negative 1. So we're just replacing the point effectively in that equation. Very similar to the parallel plane, problem number 5. Next one. Find the point, Find the point where the line r of t is 3 minus t, 4 plus 2t, comma t, and the plane 2x minus 3y plus 4z equals 6 intersect. So our strategy here is we're just going to plug in 3 minus t as x, 4 plus 2t is y, t is z into the plane equation. We can solve for t then, and then plug that t back into our line, and that should give us our point. So what we're going to get is 2x, but we're going to need 3 minus t, minus 3 times y, which is 4 plus 2t, plus 4z, which is just t. That should equal 6. So we get 6 minus 2t, minus 12 minus 6t, plus 4t equals 6. So we have a minus 8t, we have a minus 4t, minus 6 equals 6. We can move the 4t over there and get negative 12 equals 4t. You see that t is negative 12 over 3, negative 12 over 4, sorry. T is negative 3. So that's not our answer, that's the t. And now we should just be able to find r of negative 3. That should be our answer. So 3 minus negative 3, that's 6. 4 plus 2 times negative 3 is 4 minus 6, that's negative 2. And then we get negative 3. And this really should be a point. I wrote it as a vector, but it doesn't really matter. So our point really is 6, negative 2, negative 3. So clearly that's on this line because we plugged in a value of t that should just give us a point on the line. We can check, is this on the plane? Well, if you do 2 times 6 minus 3 times negative 2 plus 4 times negative 3. Does that give us the 6 that it's supposed to? So that's 12 plus 6 minus 12. 12 and minus 12 cancel. It does indeed give us the 6. So it checks out that this point is indeed both on the line and on the plane. Okay, next one. Let's see, we've got consider the lines. R of t is t, 2 minus t, 3 plus 4t, and m of t is 5t minus 3, negative 2t plus 2, 6t plus 5. We want to find the intersection of the lines. So that intersection here is a point on both. We're going to get r of t equals m. Now it's tempting to put a t in here, but it could be a different value. So for instance, like r of 1 could equal m of 2. So let's just put in an s here. And that's going to give us 3 equations and 2 unknowns. So we'll get a t equals 5s minus 3. And then we'll get a 2 minus t equals negative 2s plus 2. And we'll get a 3 plus 4t for this third component equals 6s. Let's write that a little bit nicer. 6s plus 5. Now we need to solve this. So one thing I'm going to do, how about we add the first and second equations together. The reason I want to do that is t plus negative t will cancel. So I'll get 2. On the right-hand side, 5s plus negative 2s is 3s. Negative 3 plus 2 gives me a minus 1. That gives me a 3s equals 3. 3s equals 3. That tells me if there is a solution, it has to be when s is 1. That is, we have to do m of 1 has to be the solution here. Now to find t, what I can do is plug this s into one of these equations. So how about this first one, because it's already solved for t. So t is 5 times 1 minus 3. It's 5 minus 3. T is 2. So if s is 1, t is 2. So the claim here is that if we have a solution, it has to be when s is 1, that is, it's m of 1, equals r of 2. Now, note, when we solved this, we ignored this third equation altogether here. And so it could be that when we plug in s is 1 and t is 2, that the x and y components match, but the z's are different here. So that's fine. One way to check if this works out is just find r of 2 and m of 1. So r of 2, let's see, that's 2, comma 2 minus 2, that's 0. 3 plus, it'll be 8 is 11. And then we do m of 1, plugged in s equals 1. We get 5 minus 3, that's 2. Negative 2 plus 2, that's 0. 6 plus 5, we do get the 11. So our answer here, our intersection point is 2, 0, 11, sort of same for both here. Now, I guess in principle, you just try values of t until you find ones that match. That's generally really tough, so we want a more systematic approach. Okay, next question. We want to find the angle between the lines. This is going to end up being the angle between the direction vectors. So this is going to be the angle between their direction vectors. So the first line, the direction vector is 1, negative 1, 4. It's the coefficients of t. And the other vector is going to have a 5, negative 2, 6. So we did a problem earlier on this, finding the angle between two vectors. The formula here was that theta is the inverse or arc cosine of, I'm going to dot the two vectors, 1, negative 1, 4, dotted with 5, negative 2, 6, and then divide by the magnitude of each. This is 1, negative 1, 4, magnitude, times, note that's a scalar multiplication now, times the magnitude of 5, negative 2, 6. And in our case, let's see what this gives us. Let's see, 1 times 5 is 5. Negative 1 times 2 is 2. So 5 plus 2, 4 times 6 is 24. Our magnitudes, let's see, are square root of 1 plus 1 plus 16. 4 squared is 16. Times square root of 25 plus negative 2 squared is 4. 6 squared is 36. here. So what we get is an inverse cosine of 24 plus 5 is 29 plus 2 is 31 over square root of 18 times 36 plus 4 is 40 plus 25, that's square root of 65. So I might just leave this like that. You could multiply 18 by 65, get some larger number in terms of 1 square root. Maybe you could rationalize the denominator. You could also like approximate this with a decimal either in degrees or radians for your inverse cosine. But this gives you an exact answer here. And it's not going to, doesn't appear that it's going to simplify very much. Okay. Next question. So we have a graph of x squared minus z squared equals y cubed plus y squared. So this is almost like one of those quadratic surfaces, but we have this y cubed messing things up. In any case, we can still draw cross sections, which sometimes are called a trace. Here's why this word trace is in here. So we're going to draw a cross section when y equals negative 2. All we need to do is plug in negative 2 for y. So we take x squared minus z squared is negative 2 cubed plus negative 2 squared. So that's x squared minus z squared equals negative 8 plus 4. That's x squared minus z squared equals negative 4. And it's going to be customary to sort of multiply both sides by negative 1. That'll give you z squared minus x squared equals positive 4. So customary to get a positive constant here. Now when we graph that, I'm going to choose to graph this on the xz plane. So I'm going to label x here, z here. We're going to get a graph here. This is a hyperbola, and I have to think about, does my hyperbola, and then does it open this way, sort of as the red direction, or does it open in sort of this blue direction here? So it's one or the other. I'm not going to get too concerned about drawing this precisely, but it's either sort of this blue hyperbola or the red hyperbola. To figure that out, what I'm going to do is, well, if x is 0, here I get z squared equals 4. So if x is 0, z could be positive 2 or negative 2. So when x is 0, we could get a positive 2 or a negative 2. That was going to leave us the blue. Note the red here do not have any points when x is 0. So the red, those are not that's not the correct hyperbola. So it's the blue hyperbola here. Next one. We're going to do a cross section when y equals 0 here. So again, we're just going to plug in y equals 0. So we get x squared minus z squared equals 0 cubed plus 0 squared. Well, 0 cubed plus 0 squared is 0. And so what we get is x squared minus z squared equals 0. That is x squared equals z squared. And that is x equals, well, it'd be tempting to say z, but you could actually have plus or minus z. So when we go to graph this, we're actually going to get two lines, x equals z. It's going to be this line here. We're also going to get x equals negative z is this line here. This is sort of this x here. So our cross section is an x when y equals 0. Next one, when y equals 1, same thing. We're going to get x squared minus z squared equals, it was y cubed plus y squared. So I get 1 cubed plus 1 squared. So we get x squared minus z squared equals 1 plus 1. That's 2. Graph this again on the xz plane. And again, really this is a hyperbola because it's square minus square. So I either get this blue sort of hyperbola that we had before, or sort of this red hyperbola. Again, I'm not really concerned about scale. I just want the general shape here. Now, if I plug z equals 0 this time, I get x squared equals 2. It means x should be plus or minus 2. It tells us there should be two solutions when z equals 0. Z equals 0 is the x-axis. I get two solutions. Our cross-section is this red cross-section this time. So it's the other hyperbola here. Okay, so we're going to do problem 10 now. Here we have a position function, which is really a vector-valued function or a parameterization of a curve. In our case, the x-coordinate is 1 over square root of 2 times t to the 4th plus 5. The y is 7 minus t squared, and the z is t to the 6th over 3. And so the first thing we're going to do is find the velocity. And the key thing here is that the velocity is really just the derivative of the position. So it's a velocity vector derivative position. And so we just differentiate each of these three components component-wise here. So we get 4t cubed over square root 2. Derivative 5 is 0. You get a negative 2t, differentiating 7 minus t squared. You get a 6t to the 5th over t to the 6th over 3. And we could simplify this a bit. You multiply the top and bottom by square root of 2. You get 4 over square root of 2 times 2t cubed, negative 2t. And the 6 and 3 simplify to just a 2. And then we have a 4 and 2 that will actually simplify down to 2 square roots of 2, t cubed, negative 2t, and then 2t to the 5th. So this here, that's our velocity, which is a vector. Okay, so that's velocity. Now acceleration, so that's a of t. Could write this as a couple ways. One is it's the velocity's derivative, so v prime of t, or because v is r prime, that's r double prime of t. Either way. Here I'm going to really focus on the v prime of t setup because I have v velocity from the previous question here, so I'm just going to differentiate this function. Could start with the original position and differentiate twice, but I've already done sort of half of the work, so I don't need to do that. Okay, so what we get here is we get 2 square roots of 2. Derivative of t cubed is 3t squared. Derivative of negative 2t is negative 2. And we get 2 times 5t to the 4th. And so we get our acceleration to be, this is 6 square root of 2, t squared, comma negative 2, comma 10t to the 4th. So there's our acceleration. Okay, speed. So speed, what that is that's really the magnitude of the velocity. Or you might write this as the magnitude, I guess, of r prime of t, because the velocity is r prime of t. So what we need to do is go up and get our answer here. So that's 2 square roots of 2 t cubed. So we're going to get the magnitude of 2 square roots of 2 t cubed. That y component from the velocity was negative 2t, and then the z component was 2t to the 5th. We just need to find the magnitude of this vector, which is the square root of 2 square roots of 2. I could bring the 2 inside as a square root 4. That would give me square root of 8. So 2 squared to 2 squared is 8. So we get 8t to the 6th. Negative 2t squared will give me a positive 4t squared. 2t to the 5th squared will give me a 4t to the 10th. And then, let's see, I can factor out a 4, which will be a 2 outside of the square root. You can also factor out a t squared, which will be a t outside of the square root. Maybe let's show that step here. Let's do a square root. This is 4t squared times 2t to the 4th plus 1 plus t to the, let's see, we pulled out a t squared, so that's t to the 8th. So we can pull out the 4t squared as a 2t. And then we have a square root of t to the 8th plus 2t to the 4th plus 1. That's going to actually be t to the 4th plus 1 squared. So if you took t to the 4th squared, you get t to the 8th. 1 squared would be 1. T to the 4th times 1 is t to the 4th times 2 gives us the 2t to the 4th. And then assuming, I guess really this should be an absolute value of t here, but we're going to assume t is positive here, so I'm going to ignore that. So I'll get 2t, and then I'll get a t to the 4th plus 1, because the square and the square root will cancel out. So this is our speed. Note, speed is a scalar, velocity is the vector. Okay, arc length. So I'm going to find the arc length when t goes equals 1 to when t equals 3. So our arc length, what this is going to be is it's an integral, well, from 1 to 3, really of our speed, magnitude of velocity, or magnitude of r prime. So we can just plug in the answer from the previous part. So we get 2t times t to the 4th plus 1 dt. I mean, you could go through the work and derive that again, but we already did that on the previous question, so I'm just going to use that. Now to integrate this, I'm going to distribute the 2t. And I'm going to get 2t to the 5th plus 2t. And that's a polynomial, so I can integrate that pretty readily. I get 2t to the 6th over 6 plus the integral of 2t will be t squared from 1 to 3. Note here the 2 and the 6 cancel to give a 3 on the bottom. So we'll get 3 to the 6th over 3 plus 3 squared minus 1 to the 6th over 3 minus 1. So this, let's see, 3 to the 6th over 3, that's 3 to the 5th, which is going to be 243, plus 9 minus a third minus 1. So this would be 252, 251 minus a third. 251 is going to be 753 over 3. So we'll end up with 752 over 3. So that length of the curve from the point where t equals 1 to the point where t equals 3 is 752 thirds. Next one, unit tangent vector. Okay, so the general setup here is our unit tangent vector. This is going to be, well, really r prime, but that's just v of t divided by the magnitude of v of t. So we get a vector that points in the same direction as the velocity. We have to divide by the magnitude of the velocity. That means we're getting a unit vector that points in the same direction as velocity. So let's go find v of t. We used that up here would be one place we used it. So there's this vector here. So it's 2 square roots of 2 t cubed. So this is 2 square root of 2 t cubed. That y component was negative 2t. And the z component is 2t to the 5th. So that's just our velocity vector. If you had a position function, you'd have to differentiate. And then we divide by the magnitude of this vector. Well, the magnitude of that vector, I guess I'm writing this out here. I don't really need to do that. That's the speed. We already calculated that in part C. Speed is 2t times t to the 4th plus 1. Now, I have to divide component-wise here. And so what I'm going to get, here, let's see, I'm going to get, 2 over 2 will cancel, so I'll get a square root of 2, t cubed over t is t squared, over t to the 4th plus 1 in the first component. Second component, the 2 t's will cancel, and I'll get a negative 1 over t to the 4th plus 1. Third component, I can cancel a 2t and be left with t to the 4th over t to the 4th plus 1. So this is our unit tangent vector. Oh, curvature. So curvature, this is really, I guess, dt ds. So we take a derivative of our unit tangent, but with respect to arc length. So our unit tangent vector, we can't just differentiate this because our parameter is t, which is not going to be the arc length. So you could reparameterize that with respect to arc length. That's going to get a little bit tricky. So what I'm going to do instead is just rewrite this as dt dt times dt ds, the magnitude of that, which works out to be the magnitude of dt dt times 1 over, this is really an absolute value of ds dt. Note ds dt is really just the speed. And so what we're going to get here is a magnitude of dt dt divided by our speed. So our speed again was the 2t times t to the 4th plus 1. So that's our setup here. And so now we can go and actually find a derivative of our unit tangent vector. So here's our unit tangent vector. So when you do a derivative, I'm going to write the denominator for this here. I'm going to write the 1 over 2t times t to the 4th plus 1 on the outside, and then do this derivative. So I'm going to do quotient rule on the first step, first component. So I get the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then we're going to go and say the second one, I can do the same thing. So I get the bottom times the derivative of the top, but that's 0, so I don't really need to put that, minus the top, which is, let's see, our -1, so that'd be a +1, times the derivative of the bottom, which is 4t cubed, over the bottom squared. And then we're going to get bottom, the third component, times 4t cubed, bottom times the derivative of the top, minus the top times the derivative of the bottom. Again, that's over the bottom squared. There's really our calculation. Now it's just a matter of simplifying this down some. I can pull out a t to the 4th plus 1 squared from all of the bottoms here. So we get 1 over 2t times t to the 4th plus 1. That'll be a cubed now. On top, let's see, I get a 2 square root 2 t to the 5th plus 2 square root 2 t minus 4 square root 2 t to the 5th. I just get a 4t cubed in the y component, and I'm going to get 4t to the 7th plus 4t cubed, stripping that, and then I'll get a minus 4t to the 7th. And so what we get, 2t, t to the 4th plus 1 cubed, and we get, let's see, so we'll have -2 square root of 2 t to the 5th. These two will sort of subtract off from each other. And I get plus 2 square root of 2t, comma, 4t cubed. And then here, these 4t to the 7th cancel. I get 4t cubed there as well. One thing I'll note is this t I could cancel out. And so in the end, I'm going to write, and I could get a 2. So I can get 1 over t to the 4th plus 1 cubed times, let's see, this is going to be negative square root of 2 t to the 4th plus square root of 2t, comma 2t squared, comma 2t squared. And I made a mistake here when I started, I'm noting here. So my curvature, that's really our kappa, here should be our curvature. This should be a scalar, but I'm getting a vector. So that tells me I didn't get the right thing, means I made a mistake somewhere. What I did is I did dt, so I found the derivative of the unit tangent vector with respect to time, but I was supposed to take its magnitude. So I'm supposed to take the magnitude of this. All the steps we did so far will work just fine with magnitude, but it means we've got some more work to do. I'm going to have to do this down here in the next problem. Here. So what I'm going to do, let's just keep going in green here. So I get a 1 over t to the 4th plus 1 cubed times the magnitude of this. So I have to square the first component. So that's going to give me a 2, let's see, t to the 8th, negative square root of 2 times square root of 2 is a 2, and I'll get another 2 when I square this, so that'll be a minus 4 t to the 5th, and then I'll get a 2t squared when I square the square root 2t. And I'll get a plus 4t to the 4th. Oh, and now I'm realizing I made a mistake. Things didn't work out how I wanted to. So I thought that this 4t to the 5th, negative 4t to the 5th, should cancel sort of with this 4t to the 4th. It didn't because I have t to the 4th, t to the 5th. So I'm noticing I made a mistake. When I divided by the 2t here, this term here should have been just square root of 2. Whoops. So that should just be square root of 2. And that's going to change. Let's just erase everything we've got here. So I still square the negative square root of 2t to the 4th. That's 2t to the 8th. When I square the, or to take square root of 2 times square root of 2, that's 2. So I'll get a minus 4t to the 4th plus just 2 when I square the square root of 2. And then I get a plus 4t to the 4th when I square the y component, plus another 4t to the 4th when I square the z. Note here, these 4t to the 4th will cancel. I can pull out a 2 to come out as a square root of 2, t to the 4th plus 1 cubed. And what I'm left with is, under the square root, So I have a t to the 8th plus 2t to the 4th plus 1 after I factor out that square root of 2. Note here what we get, so we have square root 2 over t to the 4th plus 1 cubed. This thing inside the square root, that's t to the 4th plus 1 squared. And so what I get here is square root 2 times t to the 4th plus 1 over t to the 4th plus 1 cubed. So I can cancel out one factor, t to the 4th plus 1, and I get a square root 2 over t to the 4th plus 1 squared. So that is the curvature, which is the answer to part F, and we just sort of spilled over here into the space for part G. That all goes, well, it goes up there, really, first. Okay, so when we do part G here, we want to find the tangential component of acceleration. There's a variety of these that we can, or there should be a scalar. There's a variety of formulas we can use. Let's switch maybe to purple color just so it's different from this. And the formula that I'm going to use is this tangential component of acceleration. It came out of our book here. Is the derivative with respect to t of the magnitude of v. That is, it's the change in speed with respect to time. So what I'm going to say is this is then the derivative with respect to t. Now our speed, I got to go back up and find that. Let's see, that was way back up here. It's 2t times t to the 4th plus 1. So it's just 2t times t to the 4th plus 1. Find that derivative. You could do a product rule here, but it's probably easier just to distribute the 2t. It's 2t to the 5th plus 2t. And so our tangential component of acceleration is just 2 times 5 is 10, t to the 4th plus 2. So that's our tangential component of acceleration. Then the normal component of acceleration, again, I would just use the formula from the book. This is, well, there's a few ways to do this. One is, this is going to be curvature here times the magnitude of our velocity, that is our speed, squared. So if you use this formula, we have to go find our curvature. Calculated here, that's the square root 2 over t to the 4th plus 1 squared. So square root 2 over t to the 4th plus 1 squared times the speed squared. So the speed was 2t times t to the 4th plus 1 here, and then we have to square that. And so our normal component of acceleration, let's see, it's square root 2 over t to the 4th plus 1 squared times 4t squared times t to the 4th plus 1 squared. The t to the 4th plus 1 squareds cancel, and I'll get 4 square roots of 2 t squared. So that's our normal component of acceleration. So that's the last bit here. There's another way to do this one, and that is there's a formula where really this an, the idea here is that you have sort of unit vectors. Really, one of these is t, one of these is n here, and then you have an acceleration vector which points in some direction. So this is a, not necessarily a unit vector. And the idea here is that you can rewrite a as this red vector here plus this blue vector here. And the red vector should be, well, it's in the direction of the principal unit normal vector. So it should be an, so sort of the scalar component, times n. And that blue vector is in the direction of the tangent, so that should be at times t. Now, if you look at this picture here, we have a right triangle. Do this in green, I guess. So we have a right triangle. That right triangle, one leg, the red leg here, the magnitude of this vector, n is a unit vector, so that length is the normal component of acceleration. The blue side here, this bottom side, is going to be the tangential component of acceleration. And then the hypotenuse should be the magnitude of the acceleration. So if you put that all together, if you already had the tangential component of acceleration and you had the magnitude of acceleration, you could use the Pythagorean theorem, and the normal component of acceleration would just be the square root of the magnitude of a squared minus the tangential component of acceleration squared. And so what we could do, here we go, find our acceleration way up here. So that was our acceleration. I'm gonna just copy this here. Scroll way back down. Whoops. Plop that there. Let's just keep this off to the side here. Okay, so our magnitude of our acceleration squared, that's really going to be this vector dotted with itself is one way. So what I'm going to use is the magnitude of a squared. That's just a dot a. That works for any vector at all here. And so what we're going to get, let's see, 36 times 2, once I square that, is 72 t to the 4th, plus 4, when I square the negative 2, plus 100 t to the 8th. And I should subtract off the tangential component of acceleration squared. So 10 t to the 4th plus 2 squared. And so what I get, square root of, let's see, so it's 72 t to the 4th plus 4 plus 100 t to the 8th minus, when I square this, I'll get 100 t to the 8th. 10 to the 4th times 2 is 20 t to the 4th times another 2, whoops, will give me a minus 40 t to the 4th, and then I'll get a minus 4. So ugly looking thing here, but 100 t to the 8th cancel, 4's cancel, and what we get is 72 t to the 4th minus 40 t to the 4th. We get a square root of 32 t to the 4th. We can pull out a 16, so we get 4 square roots of 2 t squared. You know what, we could do things this way. We get the same answer we did before. The main advantage of this method in green is we did not have to calculate the curvature here. So we didn't need the curvature. You look at the AT calculation, we just needed the speed. We found the derivative of speed here, and we needed the acceleration. So typically, if you didn't have the curvature sitting around, this green method is going to be better. If you've got the curvature, probably this purple was a little bit easier, but that curvature calculation can get a little bit difficult. Okay, next one. So number 11 here, consider a particle that has acceleration function 3t minus 4, comma t squared, comma negative 1. We have an initial velocity and an initial position, and we want to find the position of the particle when t equals 3. So our setup here is a of t equals 3t minus 4, t squared, negative 1. And so our velocity is going to be, well, I'm just going to integrate each of these, or find an antiderivative. So I'm going to get 3 halves t squared minus 4t. I get a t cubed over 3, and I get a negative t, but I'm supposed to add a constant on each one. So I'm just going to add plus some vector c1, c2, c3 here. To figure out what these constants are, I can plug in 0 and get my initial velocity. So what I get here is v of 0 equals, well, this whole vector is all 0, so that's just c1, c2, c3, but apparently that's 2, negative 1, 0. So you plop those in here, and that tells us our velocity is 3 halves t squared minus 4t plus 2 for c1. We get t cubed over 3 minus 1, 1 being the c2, and we just get a negative t there for c3. Now our position then will be the antiderivative of velocity, so we just need to integrate these component-wise. T squared will be t cubed over 3, so we get a 1/2 t cubed minus t squared over 2 is the antiderivative of t, so we'll get a minus 2t squared plus 2t. And then I'm going to integrate t cubed over 3 gives me t to the 4th over 12. Integral of negative 1 is negative t. Integral of negative t is negative t squared over 2. And again, I need to add a constant vector. Now I'm going to do something that's, I think, very typical, but maybe technically not correct. I'm going to just reuse C1, C2, C3. So these are different than these C1, C2, C3, but I've already figured out what those are, so I don't need them anymore. So I'm just going to ignore sort of the fact that I'm reusing these just so I don't have to create a whole bunch more variables. Then what I can do is do r of 0 is 0, 3, 1, but that's also, again, if I plug in 0 for t, this whole vector is 0. It should just be C1, C2, C3. So I get 0, 3, 1. And so my r of t really should be 1/2 t cubed minus 2t squared plus 2t plus the c1, which is 0. And you get t to the 4th over 12 minus t plus c2, which is 3. And then negative t squared over 2 plus c3, which is 1. So that's our position function, and now what we want really is just r of 3. So r of 3 should be 1/2 times 3 cubed is 27, minus 2 times 9 is 18, plus 6. See, 3 to the 4th is going to be, I can take 1 3 and cancel that 12 to a 4, so I'm going to get 27 fourths minus 3 plus 3. I'm going to get a negative 9 halves plus 1. And we could simplify that a little bit. Let's see, this is 27 halves minus 12. 3 and the 3 cancel, so I just get 27 fourths. Let's see, negative 9 halves, I lost my 1 there. So that's 2 halves, so that's a negative 7 halves. And then that's a minus 24 twelfths. So we should get 3 halves, 27 fourths, negative 7 halves as the position when t equals 3. Okay, so number 12 here, we want to find a vector function that's really just a parameterization of a curve that represents the curve of intersection of the surfaces z equals x squared minus y cubed and y equals x squared. So the thing I'm going to focus on is this second equation, y equals x squared, only has 2 of the variables, and it's solved for another one of the variables. So what I'm going to do is my hope is I can just let x be t. Then, because I have to have y equals x squared, y will have to be t squared. So I have an x and a y in terms of t, and now I just have to find z in terms of t. But, very fortunately, z, if I'm going to satisfy this equation, that is be on this surface, z has to be x squared minus y cubed, but x is t, and y squared is t squared. So that means z has to be t squared minus t to the 6th. So my parameterization here is just t squared minus, whoops, sorry, that's the z component. Parameterization is the x component is t, the y component is t squared, the z component is t squared minus t to the 6th. So that's just a short, sweet parameterization of the surface of intersection of, or sorry, the curve of intersection of those two surfaces. Okay. One more position function. We want to find our unit normal here, our principal unit normal vector. So what we've got here is an r of t. We want to find the principal unit normal. So what I'm going to do, first of all, is find t of t. To do that, I have to find r prime of t, and so maybe I'll just write off up here. I really want to find, first of all, t of t, which is r prime of t. Whoops, kind of mess with that. So that's going to be r prime of t divided by the magnitude of r prime of t. So it's a unit vector in the direction of the velocity, which is r prime of t. So r prime of t here, I have to do a chain rule. And you get a negative 3t squared sine t cubed. So I would get a negative sine t cubed, and then the 3t squared is the derivative of t cubed. Derivative of sine is cosine, but the derivative inside is 3t squared. So I get cosine t cubed, and then I get a 0 in that third component. Now, this particular vector I can rewrite as, let's see, how about 3t squared times negative sine t t cubed times cosine t cubed. The reason I want to do that, well, and then it is 0. The reason I want to do that is it's going to make finding the magnitude easier, because then the magnitude of r prime of t, because I have this scalar out in front, is just 3t squared times the magnitude of the rest of this, which is going to be, let's see, so it's just going to be sine squared t cubed plus cosine squared t cubed. But this is a sine squared t cubed plus cosine squared t cubed, so that's 1. So I get 3t squared times square root of 1. That magnitude is 3t squared, which means t of t here is going to be, let's see, so it's 3t squared. Well, okay, it was a unit vector in the direction of this vector, so it should just be that vector. But you can notice I'm just going to divide here by the 3t squared. So here's my r prime of t. And then I have to divide by the magnitude, which is just turns out to be that scalar out in front. Those cancel. So my unit tangent is negative sine t cubed cosine t cubed comma 0. Okay, that's t. That's not what we're asked for. We're asked for n. N is the derivative of t with respect to t here, except we need to make that into a unit vector. So what I'm going to do is find really t prime, which is the derivative of t with respect to t, and then I'm going to convert that into a unit vector that will be n.